All right, so welcome to Math 343, the math of sports. What I want to do today is give a higher level lecture on talking about how do you find what's the right statistic to look at, how do you use data to make conjectures, how do you come up with mathematical models, how do you prove these models are correct. And I want to try to do a problem that has real world applications. So this is a talk I've given numerous times. This is a really fun topic. It's also an extremely important topic. Not that I think sports is not important, but the fate of the free world, I think you really don't have to motivate why we care about solving problems like that. All right, so you can click on the YouTube link, email me if you want a copy to the slides if you're not in the class. And this just shows you the incredible gains the Germans made at the start of World War II with their blitzkrieg tactics. So they had a masterful use of tanks and very fast attacks. A tremendous number of countries and territories quickly crumbled. So it was extremely important for the Allies to get a sense of how to respond to something like this. And when you're doing this, you need to know how many tanks are you facing. So you need to know how many tanks are the Germans producing. So one possibility is for Churchill to just call up Hitler and say, hey, excuse me, we're having a meeting. We need to know how many tanks you're producing each month. Would you mind letting me know? I think we all know that this is not going to work. So how could the British find out how many tanks the Germans are producing? What could they do? Spies. So you could actually send spies. Now, one of the interesting things is if people know that you have spies there, there is the possibility of deliberately misleading the spies to then have them push false information. So one possibility is spies. The other approach is through statisticians and mathematicians. Which do you think is going to work better, the spies or the mathematicians, statisticians? Given that this is a lecture in a math stats department. Yeah, probably the mathematicians is going to work better. But interestingly, it's not enough to be right. You have to convince the people who can make the yay or nay decision to listen to you. So on Friday, we're going to have a Williams alum who's now working with the Mets, who's going to come in and talk about his job doing analytics for the Mets. And a lot of it is to try to convince the people to actually go with the recommendations. How do you find the right statistics? And then how do you convince the management? One of my favorite examples, and I might have already shared this already, is before the Battle of Midway, which was the turning point in the war in the Pacific. The Americans had cracked some of the Japanese codes, and we knew that they were about to attack something called AF-15. And we thought AF-15 was Midway. And if it's Midway, we can plan a trap for them. And that's actually what happened. It was the turning point. The Japanese had more aircraft carriers than the US before the battle. Afterwards, we had more. But Admiral Nimitz was like, you're pretty sure it's Midway? Well, what if it's not Midway? What if they attack someplace else and our entire fleet is at Midway? Oh, that would be bad. Okay. Come back when you're sure that it's Midway. And so Commodore Rochefort had one of the most brilliant ideas I've ever heard in my entire life. On a secure channel, he told Midway to break one of their water pumps. And then either on an open channel or on a code that he knew the Japanese had already broken, he told Midway in a list of just standard information, just include the fact that you have a broken water pump and will be out of fresh water in 2 weeks if it's not replaced. And a day or two later, the Americans intercepted a Japanese message saying AF-15 has a broken water pump and will be out of fresh water in 2 weeks if it's not replaced. And this was a beautiful example of getting the other side to divulge a secret. So you've got to be very careful about what information you're giving, what information you're sending. So how are the statisticians going to help? Well, after a battle, at least if you win, you can look at what's left on the field. And so this is now called the German tank problem. So you observe a couple of serial numbers, S1, S2, ... SK on captured or destroyed tanks. And you want to use this to estimate how many tanks were produced. So I give you the number observed, K. I give you the sequence of serial numbers. We are going to assume that the serial numbers are consecutive integers starting at 1. With some students, I generalize this to if it's consecutive integers, not necessarily starting at 1, and I've generalized it further with even more students. So there's a lot of still research you can do on this. Imagine you are a new company and you're trying to get business and you're talking with somebody and says, okay, we're really excited to have you. You're going to be account number 0000001. We're your first account. Yes. You might have a little trouble And so you sometimes want to hide things. You have these completely randomized numbers. Why might it be useful to have things consecutive? What could be advantageous for the Germans to have serial numbers with some kind of nice structure to it?
Probably easier to keep track of when you're constantly using them.
Yeah, much easier to keep track of, especially if you say maybe these digits tell you where it was produced, which factory. These digits tell you when it was produced. So you can quickly see anybody that was produced in this factory. We just found out that that factory had an issue with how they were making treads, and those all have to be re-examined. Or anything that's been produced at this date, it's now time for a service. And so you can still do this if you encode the serial number, but it's now more work. But there are advantages to having something like that. Has anybody ever been in a restaurant with a tip jar? Okay, have any of you been at a restaurant with a tip jar at the start of a shift? When they just opened, you were one of the first people to come in. What do you think is the status of the tip jar at the start of the shift? Of course. Yes, they want people to think that people are tipping. And so you've got to be very careful about what information is being conveyed. Just because you see money in the tip jar does not mean that people have tipped. They want people to see that this has been happening. So you've got to be very careful about what information are people giving you. This is a math of sports class. There's a lot of misleading information you can do. When people are trying to determine how much they want to pay to sign someone, a huge amount of that is a function of are other teams interested. And years ago, the Yankees screwed the Red Sox by feigning interest in Carl Crawford from Tampa and drove up the price. They had no desire to get Crawford, but by expressing as much interest as they did, the Sox committed a lot more resources than they otherwise would have had to. So really think about what information you're sending out. So the original formulation is we have numbers 1 through n. We observe k tanks. The largest serial number is m, and we want to try to estimate how many tanks there were as a function of m and k. So we'll call that n hat. So can anybody give me any functional forms of how n hat should depend on m and k? If I increase m, if I increase the largest serial number that I observe, what should be true about n? So it should be going up, right? So if I keep the number of tanks fixed and I tell you m is 100 or m is 200, I would expect that n is larger when m is 200. What if I keep m fixed and increase k? The largest serial number is 100 and I observed 5 tanks. The largest serial number is 100 and I observed 20 tanks. Where do you think n is probably larger? When you observed 5 tanks or when you observed 20 tanks?
It'll go down when you observe more K.
Okay, so we think that it should be going up with m, down with k. Can anybody give me a lower bound on how many tanks there are as a function of m and k? A lower bound. There has to be at least this many tanks. M. That's the best answer you can give me. Well, if the largest serial number I observe is m and the tanks are labeled consecutively, there's got to be at least m. There is another answer you could give that is correct. It's not as good as m. K. There's at least, I observed k tanks, so there's got to be at least k tanks, but m is the best lower bound. So I want a function for n. It's got to be at least m. So it's got to be m plus something else, right? So do we all agree? I'm looking for something of the form m plus something. And this something has to be increasing with m, maybe, and decreasing with k. Can anybody give me a guess for what might be a good functional form?
It's a little different. Didn't we do something like this where you just average out the ones you saw and multiply it by 2? Was that a different? I remember we did this a couple weeks ago where it was for a completely different example.
It was for a different example. I'm not sure what that one was. Does anybody else remember that one?
Feels similar.
I mean, it should. I mean, that's the whole point, is that we keep seeing the same thing again and again. But can somebody give me a functional form that increases with m and decreases with k?
M plus m over k.
So m plus m over k is the simplest thing you could go with. You could give yourself a little bit more flexibility and you do maybe m plus some constant. times m over k. And it gives you a little bit more freedom. Now, before we go into that formula, I'll just quickly say for explicitness, there are dangers of overestimating or underestimating. For certain problems, one is more dangerous than the other. If you're in an elevator, which is worse, overestimating capacity or underestimating capacity of an elevator? Okay, so yeah, it's much worse to underestimate capacity. So what's the problem if you underestimate the capacity? So, and it breaks. Whereas if you overestimate, well, we could have had more people on the elevator, and so we have some inefficiencies, but that's much better than things breaking. So can somebody give me either in battle a danger of overestimating or underestimating how many enemy tanks there are?
You underestimate, you're not going to bring enough tanks.
Good. So if you underestimate, you might not bring enough tanks and you might be defeated. If you overestimate, you might win that battle, but you might put in so many forces there, you might lose someplace else. One of my favorite quotes from Lincoln is, there's several different variants. If General McClellan isn't going to use his army, I'd like to borrow it for a time. So in the beginning of the Civil War, the North had numerous opportunities to crush the South, but McClellan, who was the commander of the Army of the Potomac, was just always afraid to move and engage. He always felt that he was outnumbered by Lee, and he would never seize the initiative. All right, so what I want to do is I want to talk a little bit about, first, what are the mathematical preliminaries we need for this? I'll mostly focus on the original German tank problem. I'm not going to really go into the new version with the unknown start. If you want to, the slides are there. You can also just email me for the paper. And then I really want to hit regression and conjecturing. So out of curiosity, for the Williams students here, how many Williams students have not taken a stats course? Okay, excellent. So everybody, you can check that box off. You should do this before you graduate. You should take at least one good stats class. This is the era of data analysis. And so what I want to do is I want to show how we can, using binomial coefficients, we can actually come up with a formula for the best estimate of the number of tanks. And then I want to show how we could have actually covered this ground in an entirely different way by using statistics. And statistics will actually predict what the formula should be. And again, the reason I'm doing this in the math of sports class is so much of what we're trying to do is find what is the right statistic to study something that we care about. And so while this is not directly applicable by discussing a sports statistic, it's the meta talk about how do we come up with ways to analyze statistics to glean relationships. That's what we're trying to figure out. What are the relationships? In professional sports, what are the two things we care about? Winning, money, right? And depending on who you are, the order may be different. There are some people who, I've got enough money, I just want to win championships. And so it's trying to figure out which statistics correlate with success or with revenue. All right, so mathematical preliminaries. If anybody has not seen any of these, please let me know. Binomial coefficients n factorial is the number of ways to order n objects when order matters. N choose k is how many ways to choose k objects from n when order does not matter. And the binomial theorem is expand x plus y to the n. It's the sum of n choose k, x to the k, y to the n minus k. This all good? Okay. Then we have Pascal's triangle. So whenever you're doing anything in theoretical math, you always want to ask, where does the miracle come from? And so Pascal's triangle has a tremendous number of relationships. Probably the most famous is Pascal's identity, that if I take any number and I sum what's to the left above and to the right above, I get my number. And if you want to continue to make this work, you just have diagonals of zeros over here if you want to continue. How many ways are there to choose 5 objects from 3? 0. You can't choose 5 objects from 3. There's not enough. Okay, so I'm going to prove Pascal's identity. And since this is a math of sports lecture, I will at least use a sports example. So assume we have n Red Sox fans and we have 1 Yankee fan. And we want to choose a group of k. How many ways can we choose k people from n plus 1? Well, that's just the definition of a binomial coefficient. It's just n plus 1 choose k. But I can split into 2 cases. In the first case, we're fortunate. We don't have the Yankee fan with us. 1 choose 0, we don't choose the Yankee fan. But now we have to choose k fans of the Sox. In the second case, we did choose the Yankee fan, one choose one, but now we only have to choose K-1 Sox fans. So by counting the expression two different ways, and this is essentially all of combinatorics, we come up with our formula. What's interesting is if you look at this formula, this is a lot more symmetric. Notice that all the tops add up to n+1. Notice all the bottoms add up to k. When you look at the original formula in the box, there's this asymmetry. Sometimes the tops are n, sometimes it's n+1. Sometimes the bottoms are k, sometimes the bottoms are k-1. Why don't we write 1 choose 0 and 1 choose 1 in the formula?
They're both one.
They're both 1. So unfortunately, when you drop them, because there's no need to put in the 1, it makes the formula a little bit more mysterious as to where's it coming from. Okay. So we've talked about Pascal's triangle. There's a lot of other interesting relationships you can do. What's 1 + 2 + 3 + 4? 10. What's 1 + 3 + 6 + 10? 20. This is called the hockey stick identity. I'm not making this up. It really is the hockey stick identity. When you sum diagonally to the left, the next number you get is to the right. All right, I'm going to skip, in the interest of time, the fractal stuff. And so just writing the hockey stick identity explicitly, if I sum m choose k from k to n, we get n+1 choose k + 1. So we get one row further than the last row and one more to the right. So whenever you see something like this, there's many different ways you can try to prove it. You can try to prove it by story. This is also screaming, prove by induction. So we'll fix k, and then we'll induct on n. So the first thing is when n equals k, it's going to be trivial because you'll just get 1 = 1. So now assume that we've done the base case when n equals k. So now we assume it holds for n and we want to show it holds for n+1. So this is actually the standard proof by induction. You just take the expression that you want, summing up to n+1, and then you have, well, here's my sum up to n, here's my remaining term. I just add them all together and I just use Pascal's identity. And that just gives the result. So the hockey stick identity is just an immediate consequence of Pascal's identity. This is going to be the source of the miracle as to why we get closed form expressions for everything. So we've already talked about how n hat should depend on m and k. We said it should be m plus something that maybe some constant times m divided by k. So it's the simplest guess. The answer turns out to be m times 1 + 1 over k - 1. So the constant turns out to be 1. Your guess of m over k turned out to be really good. The -1, that's going to be really hard to see. So we always want to test whenever we get a formula, is it reasonable? Can anybody give me some extreme values of k, n, m where we know what the answer is? If I observe this many tanks and n is this and m is this, I know what the answer has to be. Yes.
M's a million and k is 1.
Okay, but then how would I know? Okay, what would you then guess for n? So if m is a million, k is 1, what would you guess for the number of tanks? It's at least a million, but why is this formula reasonable? Well, when k equals 1, this is basically telling you the number of tanks is essentially twice your largest value. Well, you only have one value. So if I'm choosing n tanks and I only choose one value, if you had to guess, what value do you think I would get? The middle. So when k equals 1, that's actually a very reasonable answer. It basically says double what you have. You probably got something in the middle. Yes. Well, so if m is 1 and k is 1, then you would guess that there's, okay, so in this extreme case, you would get 2 minus, you would get 1. And you would guess that there's 1 tank. Because m is so small, the -1 is now playing a significant role. So we just did the case when k equals 1. That's one extreme. What's the other extreme for k? What's the largest k could be? N, right? Imagine you observe every tank. Well, if k equals n, if you observe every tank, what's your largest serial number going to be? If you observe every tank, what will your largest serial number be? So the tanks are numbered 1 through n. We observe n tanks, so it has to be n. And so if I take k equals n and I take m equals n, I get n times 1 plus 1 over n. All good, that's going to be n plus 1 minus 1 is n. So this formula is reasonable. When I take the extreme cases, it gives me what I would predict. So it passes the sanity checks. And so now let's talk about how you would prove this. So what I want to do is I want to calculate what is the probability that the largest observed tank is little m. So there's a couple of ways to do this. So what's the probability that the largest is little m? We know m has to be at least k, and we know it can't be larger than n. So I only have to calculate it in that range. Okay. What would it mean if my largest tank is little m? It means I chose k tanks from 1 to little m. But if I look at k tanks from 1 to m, I don't necessarily choose tank m. So I'm going to throw away all the times I choose k tanks and I don't choose m. That means I chose k tanks from the first m minus 1. How many ways are there to choose k tanks from n? That's just n choose k. And then I can use Pascal's identity to say that this is the same as m minus 1 choose k minus 1. If you don't like that, here's the second proof. If my largest tank is m, then I have k minus 1 remaining tanks that have to be chosen from 1 to m minus 1. So I can get it that way. In fact, you can use this as another proof by story of Pascal's identity. So it's a nice corollary to our work on the German tank problem. We actually get Pascal's identity. So we now know exactly what the probability is. And so what we could do is we can do expected values. So is there anybody here who has not seen expected values? Okay, so you've covered this all in your stats course. It's basically, if I give you the midterm is 50%, the final, well, no, final would never be left. Let's say the final is 40%, midterm 30%, homework 20%, class participation, whatever I need, probably 10%. Then if I want to calculate your score for the semester, it would be 0.1 times your class participation plus 0.2 times your homework and so on and so on. And so I just take each value and I multiply by the weight. And so if I want to calculate the expected value of m, I take each possible value of m and I multiply by the probability we choose that. So if I roll 2 fair die, I could, and I look at the sum, I could have anything from a 2 to a 12. A 2 only occurs 1 out of 36 times. A 3 occurs 2 out of 36 times, all the way up to a 7, which occurs 6 out of 36 times. And when you do this, you'll see that the average value when you roll 2 fair die for the sum is going to be 7. So I now want to calculate what is the expected value of the largest tank. So it's going to be m times the probability of m. So I need to evaluate this sum. Does anybody have any thoughts about how we might try to evaluate this sum? What can we do? So we have m times the quantity m minus 1 choose k minus 1 divided by n choose k. Any thoughts about what we could do or what we might want to expand? So sums in general are very hard to evaluate. What is m minus 1 choose k minus 1? My binomial coefficient. What's m minus 1 choose k minus 1? It's going to be m minus 1 factorial divided by k minus 1 factorial, m minus 1 minus k minus 1. That's going to be m minus k factorial. I've got an m minus 1 factorial and I've got an m over here. The m wants to just come on over. So the solution is to expand out the m minus 1 choose k minus 1. And when we expand that out, we want to just basically have the m move in here. I've got a k minus 1 factorial. This is almost m choose k. I need an extra k down below. Well, then if I multiply by k over k, I'm going to be able to make this, I'm going to have an m choose k. And so when I do a little bit of algebra, I now get to the point where I have a sum of m choose k. And this is where the miracle happens. This is the hockey stick identity. We can replace the sum of m choose k with just n plus 1 choose k plus 1. And now we can simplify this a little bit further. I know it's been cut off a little bit by just expanding out what n plus 1 choose k plus 1 is. And that's going to have a bunch of factorials, things will cancel. And when things cancel, we just get kn plus 1 over k plus 1. So this was just very straightforward algebra. Just expand the binomial coefficient, do the algebra. And at the end of the day, we get n. I'm sorry, we get the expected value of m is k times n plus 1. I'm sorry, is the expected value of m times 1 plus 1 over k minus 1. So that's a formula for the expected value of m if we move everything over. Well, we know numerically we have an estimate for the expected value of m. We have whatever we observe. So we can plug that in and use that to get a prediction for n. We just put in what we observe for the largest value of m, and here's our prediction. And so this is a derivation of the proof. Things are a little bit more complicated when you're doing the problem with the unknown start. If there's time, I'll come to that at the end, but I really want to talk about some of the issues with the regression. All right. Did we do a lecture on the method of least squares in this class? Okay. So when you did stats, did you do the regression line, finding the best fit straight line, and you did the method of least squares? Okay. So there are 3 natural candidates for trying to find the error. And so I believe there's a linear relationship between y and x. I believe y equals ax plus b, and I want to find the best values of a and b. So the first is I can look at the observed minus the predicted. I can look at the absolute value of the observed minus the predicted, or I can look at the square of the observed minus the predicted. Can somebody give me an issue with the first one? Just observed minus predicted. Why is this bad?
If you have a bunch of positive and negative values, you can get 0 difference.
Yeah, so if I observe 2 points, one at the bottom left and one at the top right, what would you say is the best fit line between bottom left and top right? Yeah, the line going through them. But I could actually draw the line from the top left going to the bottom right, and the 2 arrows would perfectly cancel. And so if we don't have non-negative quantities, we are in a situation where positive errors and negative errors can cancel. So the first is a terrible measure of error. So it's down to either absolute values or squares. So did they tell you why squares are better than absolute values? Or is this more like Moses came down from Mount Sinai? In addition to laws on how we should behave towards each other, he also had laws for statistical inference. And thou shalt use squares. So did anybody take a class where they told you why we use squares and not absolute values? Okay, so why do we use squares and not absolute values? Do you remember?
The absolute value function isn't differentiable.
The absolute value function is not differentiable. So we've just spent all of this time taking all these calculus classes. It would be wonderful to actually use them other than just checking off that I've done calculus classes, so you'll let me take classes that have the prerequisite. Let's use it. And it turns out if you know calculus and linear algebra, you can write down best fit values for A and B as explicit functions of the data. It's a really nice 2x2 matrix problem. If you use absolute values, we have to use numerical techniques to find the answer. The way I like to phrase it is, if I'm being hired, I like to use squares. If I'm hiring someone, I want them to use absolute values. The absolute values are less sensitive to one bad data point. One bad data point can have a tremendous impact when you're using squares, because 1 error of 2 is much worse than 2 errors of 1. Okay, so I'm not going to go through, but you can write down an explicit formula. You can set up matrix equations and explicitly write down what A and B are in terms of sums of everything. So that's a wonderful thing. There are a lot of relationships that are not linear, but they can become linear after you use a logarithm. And this is one of the 2 reasons why we love the log function so much. So if I have, for instance, y equals b x to the a, if I take logs of both sides, now I get the log of y is a linear function of the log of x. And so one of my favorite examples is Kepler's 3rd law. So Kepler had 3 laws of planetary motion. The first is the planets move in elliptical orbits with the sun on one of the foci. The second is if you draw a line from the sun to the planet, it sweeps out equal area and equal time. And the third, the more complicated one, is the square of the period is proportional to the cube of the semi-major axis. And so he discovered these empirically. You can discover this very easily using statistics. So the first is, rather than saying the square of the period is proportional to the cube, I might as well just take the square root of both sides. I can always have one of the exponents be to the first power and just adjust the second. So it's to the 1.5 power. So here is the list of data. I will sadly not include Pluto. I'm going to measure distances in terms of astronomical units. So the Earth on average is 1 astronomical unit roughly from the sun. It just makes units nice. And I'll measure periods in years. So when you look at this, there is one planet that should be special when you look at its distance and its period in terms of trying to figure out what that constant b should be in t equals b L to the a. What planet should we look at? Earth, right? These are deliberately designed so that the units work out very nicely for Earth. And so in this unit of measurement, b should essentially be 1. And so if we actually now try to find the best fit line, we get a equals 1.49986. Okay, that's basically 1.5. And b is essentially 0. It's amazing how well this works. And so you can numerically see Kepler's law, and we're talking about on the order of 8 data points. Phenomenal how good of a fit this does. If there is time at the end of class, I'll talk about how in the 1800s they actually predicted where Neptune should be because of issues with the orbit of Uranus and other planets, and just the mathematics involved in doing predictions like this. This is what we want to do. We can do this for sports, we can do it for finance, we can do it for anything. The goal is I want to make predictions. And what I want to do in this class is I want to teach you how do you make predictions. And there's a couple of ways. One way is coming up with a model, showing that the assumptions of the model are reasonable, and then actually solving the model or numerically approximating and getting that. The other is to use statistics and try to make inferences. The danger, of course, is that maybe what worked in the past may not work in the future. Just because the sun rose yesterday does not mean the sun will rise tomorrow. My favorite example is, has anybody read The Black Swan? All right, so the best example from that is, a turkey is born and trying to make sense of the world. And after a while, the turkey realizes there are these strange two-legged creatures that seem to be devoted to its welfare. Every day they bring food and drink. And this happens throughout May, June, July, August, September, October. And then what happens? So, well, they might wait till Christmas, but yeah, sometime around then, then the winter holidays come and there's a massive change, and all the stuff that you thought was giving you a sense of what the future would be like, all of a sudden the situation changes, and there's a way to interpret what was going on. They weren't feeding you for the benefit of you. They were fattening you up. So be very careful when you're trying to make inferences. Do you have any reason to believe that the assumptions that you made in the past will continue to hold? Be very careful about that. All right, have we done this image yet in this class? All right, this is one of my favorite bad statistics. Who knows what statistic I'm about to mention? So but you can't remember the name, or? Yes, it is a person. So it is Smoot. So he was a undergraduate at MIT a couple of decades ago, and he was pledging a fraternity, and they wanted to know how many Smoots would it take to get from one end of the bridge to the other. So they picked him up, put him down marked, picked him up, put him down marked, and they did this, and they found it was 364.1 Smoots. I love the plus or minus in here, to get from one end of the bridge to the other. The city of Cambridge did not find this amusing, so they erased all the Smoot marks. The fraternity did not find this amusing, so they did this again. Eventually, Cambridge gave up, and it's now been institutionalized and is part of the local flavor of Boston. They have official Smoot markings on the bridge. I recently jogged that when I was in Boston for some lectures I was giving. And when there was a car accident on the bridge, they actually give the location in Smoots where the accident happened in the police report. Is the Smoot a good statistic? Is this a good unit of measurement? This is not a hard question. All right, why is the Smoot such a bad unit of measurement? How big is one smoot? Does everybody happen to have a smoot on them? Is Smoot's height constant throughout time? Or as he gets older, is his height going to change? It's a terrible unit of measurement. We want to find good unit of measurements. How many of you have ever seen the birthday problem? So I will be careful. I will just hope my wife doesn't listen to this. Years ago, when we had an event for perspectives on campus, I convinced admissions that everybody at my table for the dinner should get free tuition at Williams, all expenses paid, if there were not two prospective students in the room with the same birthday. And the admissions office was a little concerned about promising that at first. And I said, I'll pay 10%. Yeah, I'll have some skin in the game. There were over 100 students at the event. I'm not worried. Does anybody know the answer to this? So how many people do you need to have at least a 50% chance that two people have the same birthday? Roughly 30 is way too high. Around 22, 23. So the probability with over 100 people is extremely high. I was not worried. You can sniff this out by doing some nice analysis with Taylor series and whatnot. If there are D days in the year and you assume every day is equally likely to be a birthday, you could get D to the 1/2 square root of log of 4 as the number of people you need to have a 50% chance. As a nice aside, because this is a math of sports, birthdays are not uniformly distributed among professional athletes. Have we talked about that in this class? So for instance, in hockey, people are more likely to be born at certain times. Does anybody know why?
It's a birth year cutoff.
Yes.
At the start of the year, you're relatively older.
Yeah, so for a lot of things, if you're born at a certain time, you want to just miss the cutoff so that you're one of the biggest kids in the league that you're playing in, because when you're young, that will give you, on average, more height, more weight. It will give you the chance to shine more in front of the coaches, so you look better, so you get more playing time, so you get more special training, and it propagates all the way up to the professional leagues. There is not a uniformity in distribution of birthdays. Malcolm Gladwell, in a wonderful book of his, I'm blanking on the title now. Outliers, thank you. Goes through, he replaces the names of all the kids in the Canadian Junior Hockey Championship final with their birthdays. And everybody is either January, February, March, or April. There's nothing in the play born later than April. What if we didn't know this? Well, we could actually do some numerics and try to do the best fit line. We could assume some kind of logarithmic relationship. And when we do this for the birthday problem, we can actually get the square root of the number of days coming out very naturally just by looking at the data. And that's one of the things I want you to get out of this. This is a math of sports class. If you become a professional statistician for a sports team, remember me when you have those tickets. You need to find the right statistics. There is a tremendous amount of data. Even if you can't theoretically prove something, can you sniff out relationships? We can solve the birthday problem. We can solve the German tank problem. I like doing these examples because I can show you the statistics matches with the theory. But can you at least come up with something interesting by looking at the data? Does it come up with something worth investigating? So let's try to do the German tank problem. So the first thing I did for the analysis was very reasonable, but horrible results. I said, well, we know we have to have at least m tanks. So let me try to plot n minus m as a function of m over k. And got terrible results. And probably when we develop the theory of the method of least squares, we don't actually have the theory taking into account the fact that you can subtract off things like that. It's not looking at the right thing. And so be very careful when you use a theory that you use it the right way. It's natural to look at n minus m, but I'm mixing my independent and dependent variables in something like that. So be very careful. What's 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 and so on and so on and so on? If I add all the powers of 2, I get yes? No, but I'm going off to infinity. 1 plus 2 plus 4 plus 8. What should I get if I add them all up? Minus 1. Because the geometric formula is the sum is 1 over 1 minus r. R equals 2. So the sum of all the positive powers of 2 should just be -1. It's so large, it goes past positive infinity, comes in through negative infinity, and peters out just when it gets to no. You can't use the geometric series formula to sum all the powers of 2 because it assumes that the ratio is less than 1 in absolute value. Be very careful when you use things that you use them only in places you should. I'm not going to go into this slide over here. Let me just talk a little bit about some of the implementation issues and how we can use stats to sniff things out. So I'm going to plot n versus the maximum observed tank m for k equals 1, and then we'll do k equals 2 and maybe k equals 5. And so my theory says that n should be 1 plus 1 over k times m minus 1. So when k equals 1, I basically get n should be twice m minus 1. And I'm going to do somewhere between 1,000 and 10,000 for the number of tanks. And I'm going to do a lot of observations. I'm going to see how many times do I have different values of n. So again, I'm going to choose maybe one tank. Maybe I choose n to be 2016. Maybe I choose n to be 5400. Maybe I choose n to be 8888. And for each choice of n, I choose one number from 1 to n, and I record that. So each of these dots is one outcome. And I try to find the best fit line, and the best fit line I get is 0.784m plus 2875. Do you think this is a reasonable best fit line? So I gathered data from between 1,000 and 10,000 tanks. Does anything bother you about this predicted best fit line? So I want to try to use this for all values of n. Yes.
You see a tank with serial number 1, guess like almost.
Okay. So if I have a very small serial number, I'm going to be inflating that by a tremendous amount. What else?
The line of best fit on the graph coefficient B is definitely not. Right? Like that looks like it's going to go over 0.
Oh, true. Yeah, that does look so. Maybe there's a typo in that. Oh, good catch. But I claim there's actually another coefficient that is even more shocking. Yes. Yeah, if you keep taking large and larger values, this is predicting that the number of tanks in the limit is about 0.784 times the largest serial number observed. What did we know was our minimum number of tanks? Has to be at least m. So this formula might do a decent job between, say, 1,000 and 10,000, but it can't be right beyond. If we try doing 2 tanks, then theory is 1.5 m minus 1, we get 0.964. It's still bad. If we try 5 tanks, we finally at least get a constant above 1, but it's still bad. The reason this is doing such a bad job, and again, the reason I want to do this is I want to just highlight how easy it is for you to misapply statistics. What we're doing is in these simulations, we're choosing n, then we're sampling 1 and we're recording the largest tank observed. M should be the variable on the y-axis and n should be the variable on the x-axis. When we were doing our method of least squares, n is now the input and m is the output. We switched things. And so what we really should do is we should rewrite things as m as a function of n. And so if we rewrite things as m as a function of n, we now get a much better formula. We get m is k plus 1 over kn. And so when k equals 1, we get m is basically I think that's a typo. I think it should be I think k over k plus 1. So I wrote it the wrong way. It should be k over k plus 1 n. So when k equals 1, the theory is m should be 1/2 n plus 0.5. We do the best fit, we see 0.496. When we do k equals 2, it should be k over k plus 1. I've got it the wrong way. It should be 2/3. We're seeing 0.667. When k equals 5, we are predicting it should be 0.883. We see 0.828. So when we plot things the right way, we're actually seeing terrific results. And so this is supporting the theory. Another thing we could have done, if we really wanted to plot n as a function of m, is for each choice of n, do a tremendous number of experiments and average. And so now each dot over here represents 100 runs for each n. And when you average like this, it actually now does a very good job of predicting. It cancels a lot of the noise. So there are tricks you can do. All right, for the last 5 minutes, I want to end with the shocker. This was doing things for specific value of k. We can use statistics to guess the functional formula as a function of k. So what I'm going to do is for each choice of k, I'm going to plot the slope in n equals a times m plus b. So I'm going to do my method of least squares, and I'm going to find the best fit value. When you look at this plot, can anybody look at this plot and tell me the functional form? Okay, so what can we do to the data so that we might be able to detect the functional form? What transformation? So if you get nothing else from the entire semester, please take this away. You should have a Pavlovian response. What transformation should you do to the data? Log, plot the log. Take the log of each and plot that. Ooh, okay, here's a log plot. I understand what shape that is. This is the power of looking at things the right way. Your original data might be very messy, but if we do a log transform, we often make it very nice. So the x-axis is the number of observations. It's the value of k. And down here, we're plotting the value of a minus, the log of a minus 1 versus the log of the number of observations. Why am I doing a minus 1? Well, we know the slope has to be at least 1. So in general, when you know some information, you can often throw it away. If I didn't want to do that, I would just be shifting things a little bit. So I'm plotting a minus 1. Now, the slope is supposed to be 1 plus 1 over k. If I subtract 1, I get 1 over k. What's the log of 1 over k? So who remembers their laws? The log of 1 over k is minus log k. So if I'm plotting the log of a minus 1 versus the log of k, I'm plotting negative log of k versus log of k. Oh, that's basically a line with slope negative 1. And so if you look at what's going on here, if we look at the log of a minus 1, the best fit line is negative 0.999 log k minus 007. If you do remember your bond history, he did start off, it's completely coincidental that we're getting 007 over there. The key fact is that we're getting 0.999, no, I'm sorry, negative 0.999. What this is telling us is just by looking at the data, if we have to try to predict what do we think the functional relationship is going to be between n and m? If we think n is some nice function of k times m, this is telling us that function should be 1 plus 1 over k. We got that without doing any theory. We got that by just doing a couple of values, simulating things, and then using our knowledge to predict. So when you leave Williams, or when you hopefully come to Williams, then eventually leave Williams, you will have a variety of problems you will want to study. Sometimes you'll be lucky enough to have a closed form model that you can solve. If that happens, please let me know so I can record it in my book. It has not happened often. Most of the time, you will have something very complicated that you will try to get some gross overall features. I still remember one day, one of my students called me and said, thank you for forcing me to always think about extreme cases. When I plugged that in, something looked really, really bad for the investment strategy. And it turns out we had dropped a minus sign somewhere. And just doing these very simple sanity checks, caught a horrendous mistake. Try to see what you can do to see if the formula is reasonable. But the biggest thing is you need some way to shine and distinguish yourself from other people. So when you're looking at sports analytics, you have to come up with what is a statistic that's meaningful, that correlates well to winning or revenue that other people have missed. Or are people evaluating statistics the wrong way? Does anybody know how a walk was originally scored in baseball? It was originally scored as a pitcher's error. think about the difference in how you reward things if a walk is considered a pitcher's error. So the batter did nothing valuable. It was all just, oh, you just happened to be going against a really bad pitcher. So new statistics that have popped up in recent years have been crediting batters with how many pitches do you see, and you're wearing out the opposing pitcher. How valuable is that? You may have gotten out, but you took up 9 pitches, and that really helps us get to the weaker part of the bullpen. All right, so I think this is a good place to stop.